So here we're going to go through some examples of full hypothesis tests. One where I've outlined the steps piece by piece, and then the second one I just kind of left blank, but we'll still go through those pieces. But I'll just kind of show you a different way of, I guess, organizing it. It's kind of disorganizing it with that one. Okay, so let's talk about what we're given in the question here. So a current antacid provides relief for 70% of people who use it. So that right there, the current antacid, so that's what's happening right now. This right here is a population proportion. I know that because it's not attached to any sample size. It's just, that's basically what's printed on the bottle right now. 70% of people feel relief from this antacid. So that's our current value. A pharmaceutical company has a new drug and they want to test whether it is more effective. So I'm just I see that word test there. Test and evidence is what I look for, and we want to test that it is more effective. So they run a study with 100 randomly selected patients. 75 people experienced relief. This is my sample data. I have my sample size. I don't have my sample proportion quite, but it is there. My sample proportion would be that 75 out of 100, which is a 0.75. So my sample proportion's there, but I just have to make it a fraction first in order. Is this evidence that the new drug is better? And I'm going to highlight that with that same evidence is what I'm looking for, and the new drug is better. So just to go back to that previous page and what I said would be given, I said we'd be given a sample size, which is that 100, p-hat, which is that 0.75 coming from 75 out of 100, assumed proportion, we assume 70%, and then that wording for the alternative where I said evidence or test, we want to show it's more effective or that the drug is better, which means to make it better, that means more people get relief from it. So we want to see a higher proportion of relief. Let's say it that way. Okay, so taking those pieces, let's make our hypotheses. Null hypothesis is going to be P equals. Alternative hypothesis, we have P. So with that, I just copied down the structure that we had originally printed on our paper. And now I'm going to fill in the blanks. So we want to see the proportion is higher than before. So I want to have a more than symbol here. And then we're using that assumed population proportion of 0.7 or 70%. So this just shows me we assume the proportion is staying at 70%. Like we assume it's just as effective before. But alternatively, we want to prove that it is significantly larger than 70%. So more people are getting relief. More than 70% of people are getting relief from this new drug that's being used. Again, as soon as I see that sample proportion in my information, I just ignore it. I ignore it until I get to calculating p-value, which is step 4. So everything else is based on this assumed proportion of 70%. Because what I want to do is eventually compare these two numbers, and I compare it by setting up everything around that 70%. Okay, checking conditions. We need to have independence. We need to have randomization. And we need to meet that sample size. Okay, so independence good, randomization were really good. They told us it was a random sample. Sample size, we're going to take our sample size of 100 and multiply that with the 0.7 from our null hypothesis. So we get 70. And then we take 100 times 1 minus 0.7, which is a 0.3. So we get 30. Both of those are more than or equal to 10. So we're all good for sample size. Okay, set up the sampling distribution of proportions and find the test statistic. So our mean, we just copy the proportion from our null hypothesis, 0.7. Standard deviation, we're taking the square root of 0.7 times 0.3 over 100, which is a 0.0458. And then for good measure, we'll find our test statistic, which is going to be, and actually, sorry, I only slightly lied, mostly because if I'm doing a hypothesis test and they don't ask for the test statistic, you don't need p-hat until p-value, but technically we need p-hat here. So we're going to take our sample proportion of 0.75, take away our mean, divide by our standard deviation, and throw that in a calculator for 1.0917 is what I got there. Again, rounding can make things a little interesting since I rounded that denominator, but I'm not going to be using the test statistic, so I'm all good there. Okay, calculating the p-value. This is where, when we get to this step, a lot of students think, wait, how do I do p-value? And what can help is as soon as you're asked for p-value, think about Statlet. That's what we're going to use. So calculating the p-value here, we're going to go to Statlet, and we want a normal distribution. I have my mean of 0.7, standard deviation of 0.0458. Plot that distribution, and then as I'm here, and in fact, often I draw a picture myself first. Let's even do that, because sometimes it can help to draw the picture for yourself first so you know what to expect before just plugging in numbers. If you can just get to the technology and plug in, absolutely you don't have to do this step. But I kind of like to piece things together before I end up plugging in numbers. So I know 0.7 is going to be in the middle here. And then what I want to do is my cutoff of 0.75 is going to be on the right-hand side. And I'm just going to confirm that I am in fact running a right tail test. So because I'm looking for p more than 0.7, I know this is a right tail test. And with that, I'm going to be finding the area to the right of 0.75. So with that in mind, I'm going to go to Statlet, because this area right here, that'll be my p-value. So with that, I go, and I know it's a right-tailed test, so I'm going to do area to the right. My cutoff is going to be a 0.75. And that area is going to be a 13.75%. So p-value equals 0.1375. So that's a calculating or more finding the p-value step. Next, I need to make my conclusion, and there's kind of a middle step there where we evaluate the p-value of is it small or not small. So what we want to do is compare the p-value to our significance level. Now, if I go back to the wording of the problem, they don't mention significance level at all. And what that means is that I go ahead and assume significance level is 0.05. We'll look at scenarios where they tell us exactly what it is, but for this, because they don't specify, we automatically use a 0.05 every time. So with this, my p-value is a 0.1375, and I want to compare it to 0.05. And if it helps, because sometimes comparing decimals can be difficult, you can always change these into percentage form, because we just want to know which one is larger than the other. So if changing it to percentage form helps, absolutely go that step, because it can be easier to see that 13.75 is larger than 5 than just seeing the decimal form. But all of this to say that p-value is larger than the significance level. So what that tells me is the p-value is not small. Which means we're going to fail to reject the null hypothesis, which means there is not evidence for the alternative. So what's happening here is we saw something that was fairly likely under this distribution. It wasn't far enough out into the tail. So that means seeing 75% is not significantly larger than 70%. So let's write our conclusion. I'm going to start it off by stating that fail to reject the null hypothesis. And I'll say with a p-value of 0.1375, there is not evidence. And then with that, I'm going to go back to the wording of the problem and just kind of remind myself what that alternative hypothesis represented. So we wanted to test whether it is more effective, or is this evidence that the new drug is better? And we're saying it is not better. It is not more effective. So there is not evidence, that the new drug is better. There is not sufficient evidence to prove that the new drug is better. That's something we could throw in there. If I wanted to put in, like, not sufficient evidence. Yeah, again, so many different ways we can word this, but this gets at the idea. We state whether we reject or fail to reject. We state our p-value. We say there is evidence or there is not evidence. And then we have some wording that connects back to our alternative hypothesis. And that right there is a full hypothesis test. All right, let's go through another one here. And it's a longer video, but we'll just keep on going so you get two examples together here. So a company develops what it hopes will be better instructions for its customers to set up their smartphones. The goal is to have 96% of customers can succeed. And the company tests the new system on 400 people, of whom 376 were successful. Is this strong evidence that the new system fails to meet the company goal? So is this evidence the new system fails to meet the company goal? So let's see what we have here. We have this expected or this assumed proportion of 0.96. We are seeing a sample size of 400. And from that sample size, we're getting a sample proportion of 376 out of 400. Which is going to be a 0.94. And we want to show that this new system is failing, so it's essentially that it's going to be smaller than that 96% success. Okay, and if we wanted to, we could think about alpha at this point. If we wanted to think about our significance level, they didn't state a significance level here, so we can just go ahead and assume it's 0.05. Okay, so I didn't outline the steps here, but let's go through this hypothesis test of we'll want the null and alternative. So I kind of set up my structure there. So we're assuming a 0.96, so 96% success rate, and we want to show that it's failing to meet that success rate, which means we're significantly smaller than 0.96. Next up, we need to check the conditions. So independence, randomization, and sample size. So we're good for independence, randomization, and then sample size. I'm going to take my sample size of 400 and multiply it by 0.96. I'm also going to take that 400 and multiply it by 0.04 from 1 minus 0.96. And that's going to be a 384 and 16. Oh, so we just make it over that barrier there with that 16, but we're good to go. Next up, I'm going to set up the parameters for the sampling distribution. I'm going to skip over the test statistics since they didn't explicitly ask for it. I wrote this. I'm going to skip over it because I didn't ask myself for it. Okay, the mean is our population proportion that we have in our hypothesis of 0.96. And then for the standard deviation, we'll go square root 0.96 times 0.04 over our sample size of 400. And that's going to be a 0.0098. So for finding our p-value, what this means is we're setting up our distribution. We have our mean and standard deviation. It's all going to be centered around that 0.96. And now is the point where I want to see what's happening with my sample proportion, which is landing off to the left here. And because we want to prove that the proportion is smaller than 0.96, we want to look at that left tail. And that left tail is going to give us our p-value. So to get p-value out, we're going to go to Statlet. I'm going to set up my mean of 0.96, standard deviation 0.0098. And then we're going to go area to the left, and we're going to look at 0.94. And that is a 2.06%. So ends up way out there, which maybe you were thinking, 94% and 96% are close together, but that's where we need the statistics to help out and kind of evaluate the spread. Where it's coming from is we have a pretty large sample size here, whereas that last example, we were comparing 70% and 75%, but we only had a sample of 100, so that allowed more variability. We had a much larger standard deviation there. So that's where it's not just a matter of what number smaller or larger, it's if it's statistically, this is going to be tough, statistically significantly apart from each other. Okay, let's continue on. So I want to compare that value to alpha, which is 0.05. And again, if it helps to switch to percentages, so that's a 2.06%. And we're comparing that to our significance level of 5%. And what we're seeing is the p-value is smaller. So we're seeing the p-value is small. And these are all just little notes to myself to kind of connect to what we talked about in the first videos. But the p-value is small, which means we reject the null hypothesis, which means there is evidence for the alternative. We're going to throw out that null hypothesis, and we can now claim the alternative. So my last step here, we reject the null. This is always the scenario we're looking for here. This is where we found the evidence that we were looking for. So we reject that null hypothesis, and then with a p-value of 0.0206, there is evidence. Of course, this isn't great. So their system failed is what we have evidence for. So that proportion was significantly less than 96%. So there is evidence the new system fails to meet the company goal. Okay, so even without the guided steps, I still go through each of those pieces. They're all required for running a hypothesis test. Things I could have left out here, I could have left out the picture. That's not necessary. I could have left out this information was more for me. But everything else would be needed. State the null and alternative, check conditions, set up the distribution, find that p-value, and then writing a conclusion. But if it isn't asked for, the test statistic is not necessary for this process here.